Okay, I'm going to talk a little bit more about things that are in GSAS-II. And this is going to be a little bit of a collection of stuff. There. Okay, we heard a little bit about this morning about calibration of images. Let me tell you about the story behind that, history of it. Here's what the issue is. The issue is, where is the incident beam on the detector? You have a detector, you have an incident beam, it hits the detector someplace. You determine that by looking at the rings from a calibration material, lanthanum hexaboride, or I forget what it is, sodium behenate or something like that. It doesn't make any difference, but you have to know what the lattice parameters of that stuff is. And you also have to know the wavelength of the radiation. Seems like a no-brainer, but indeed you do have to know what it is. So the question is, where is the incident beam on the detector? Well, there's software out there, some rather popular and well-known software that does not get it right. Because Fit2D in particular, there's another one called Data Squeeze, assumes that the center of the diffraction ellipse is the position of the beam. This is false. This is geometrically false. This is worse, because the proof of it is in fact really rather old. 1822, there was a paper written by one G.P. Dandelin in this journal, Memories of the Académie Royale de Brussels, second volume. And here's his drawing, which shows the construction that you use to find where the beam is on the detector. Basically, we have a cone, which is the Bragg cone for a particular reflection. You have a plane. It's a little hard to see in his sketch, but there is a plane here which intercepts that, and you get a conic section. Conic sections were a really big deal at the end of the, I guess it was 16th century, beginning of the 17th century. Maybe it's 18th, yeah, whatever number it is. So this was really a big deal because it all had to do with things with the orbits of the planets around the sun and all that sort of stuff. Were all conic sections, and everybody was thrilled about it. Anyway, so his construction is that you place two spheres, one above the plane, one below the plane, so that the sphere touches the cone, and the center of the sphere is the cone axis passes through the center of the sphere, and it also touches the plane there. And then you have another sphere which is below the plane that touches the cone and touches the plane, and the two centers of the sphere then determine the line. That is the cone axis. That's the beam. So this, my point is, this is not something new. This is really, really old geometry. And this is the construction that we use in GSAS-II for this particular issue. Two other pieces of software we know get it right. One is IRENA, which is Jan Islowski's small angle scattering analysis system. And in there's a calibration of detector positions, and it does it correctly. And PYFAI also gets it right. Had proof that just literally last week. What it takes is somebody willing to take a tilted detector image and see if you can calibrate it. Because if you have a detector image where the detector has been tilted like 5 or 10 degrees, Fit2D simply falls flat on its face because it has no idea what to do with it. Okay, here's another sketch of it. You'll see these in your notes, so you can look at it. But the point is that the parameters in GSAS-II is the sample to detector distance. That's this one right here. The tilt angle, that. The azimuth angle, which is around which axis it's tilted, and the position of the beam on the detector, which is, I guess it's right about there. Incidentally, the two spheres touch the plane at the two foci of an ellipse, interestingly enough. Okay, so here is the detector image in which the detector was tilted 45 degrees to the incident beam, and you can see that the rings are ellipses, and that the calibration, which is the little blue line through the rings, gets it spot on, correct. And here's the position of the center of the rings as you go from one ring to the next. Nowhere near the beam center, which is there. So I should say that. So all you need to know is what the stuff is, because that establishes the lattice parameters and the positions of the lines and the wavelength. Okay. Now, there. Knowing that and having an accurately positioned detector, the next issue is, what is the polarization of the X-ray? For synchrotrons, it's somewhere around 1, somewhere between 0.9 and 1. Where it is exactly actually matters for some kinds of measurements. And we hit upon this rather easy way. There's lots of hard ways to determine this. You put a little crystal in there and you rotate the crystal around, and you measure the intensity as a function of the azimuth angle off a particular plane, and the variation then gives you the polarization correction. That's a horrible way to do it, because you have to put this funky little apparatus on your beam line and drive it around measuring this remotely, because you can't be in the hutch while you're doing it, and so forth. So we hit upon this rather easy idea, which is you take something which is amorphous. A glass microscope slide is absolutely perfect for this. It's the right sort of thickness, scatters pretty well. And when you do, you get a curve that looks something like that. This is about what the image looks like when you do it. And by the way, this one hasn't been corrected for polarization, because you can sort of see that there's sort of an asymmetry to it, up, down, relative side to side. So this is the function for the polarization correction. And you notice that it depends not only on 2 theta, but also on the azimuth. And from this, the maximum correction is at an azimuth of 90 degrees. So what we do is we create a small mask there, which is either used or not used in the integration. So if you use it in the integration, you'll get one curve. If you don't use it in the integration and polarization is incorrect, you get a slightly different curve, because this spot with this high polarization correction has been left out. And you do it over a narrow band to improve the signal. So if you look very carefully at this plot, and it's a little hard to see, but perhaps you can see it, is here the 2 integrations are slightly different with a polarization of 0.95. And here again, they're slightly different again with a polarization of 0.85. When you adjust the polarization to be that number, the 2 integrations are exactly the same. And that's how we can measure the polarization. You simply change this value until these 2 match. And you can do this by a little least squares routine, which in the middle of that least squares routine is an integration of the image. Anyway, so that's that. That leads to the next topic, which is, and I think we saw an image about like this earlier, somebody, The detectors are not uniform. They're constructed of strips of material, each of which has slightly different responses to the X-rays, depending on how they're made. They're slightly kind of be a little tilted a little bit. And again, you start with this glass microscope slide image, because the thing you know about this is because it's purely amorphous, this should be uniform around the azimuth. Okay, there's going to be a variation this way, but it should be uniform around the azimuth. So if you have the polarization corrected correctly, then any variation you're going to see is going to be because of the response of this detector behind it. So what you do is you take the image, you integrate it, you take that integrated curve and use that to calculate a new image, which is basically the average of the actual image. Subtract one from the other, and the difference is the gain math. Now, that's a whole lot easier than some of the other kinds of procedures that people have suggested, where you have a detector which is offline, you have some sort of uniform source of X-rays, probably at the wrong wavelength, or some other wavelength, and you try to measure the response directly. This is easier. It does have a little bit of a problem right here around the beam stop. And that actually, there is an additional technique that uses 3 images which are displaced sideways, about 5 centimeters that way and 5 centimeters that way, and one in the middle. And for that, you can use that to clean this up. Notice that as you go across this detector, first of all, there's a funky little gap in here between the set of panels that are above and below. I have actually seen some of these things where the individual panel is slightly skewed a little bit. This is the beam stop. And there's a variation between sort of the, I guess this is the lowest to the highest, so something like about 3 or 4%. And this is so easy to do that it's something that should be done fairly often, because these detector responses actually change with time, depending on how often they've been used and what they've been used for. And so that's that part of the story. Okay. Oops. Texture analysis. Now for something completely different. So what is texture? Well, non-random crystallite grain orientations. Now, this may be because the powder grains themselves have a shape to them. Pack them, they pack according to the shape some way. And you're sort of then presented with a sample. Grain orientations aren't uniform. Or it may be a piece of steel that's been rolled in a rolling mill, and the rolling action induces a texture in the steel. And that's actually of interest to people, because they want to know how textured it is, for various reasons, because it affects all the physical properties of the material, depending what the texture is. These things are characterized by something called a pole figure, which is, the text says, a stereographic projection of some selected crystal axis, say 100, down some sample direction. And in the case of a rolled steel plate, it might be to the normal to the plate, something like that. Or if it's a wire, it'll be down the axis of the wire. Then, if it's a wire, usually the grains inside are oriented so that, in case of something like copper, the 100 axes are all lined up along the wire axis. And then the pole figure will then show a high spot in the center because of all these oriented axes. You also get a rim because perpendicular to that 100 direction is entirely equivalent to 010s and 001s this way. So that gives you the rim on that. Okay, this is then described by something called an orientation distribution function, which gives you the probability of the orientations of the grains within the sample with respect to the sample axis. This thing is a four-dimensional object. There we go. So you measure it by diffraction. And instead of getting uniform rings, you get rings which have high spots and low spots. And as you rotate the sample around, these high spots and low spots will move around on the rings, just depending on which set of planes happen to be there for diffraction. Okay, so that's how you measure it. Again, here's the function of the correction to the intensity, which is this guy, depends on the reflection. It also depends on the direction with respect to the sample coordinates, whatever it happens to be. And this thing then is a sum of symmetrized spherical harmonics. And you say, what are spherical harmonics? Think atomic orbitals. It's the same math, except there's two sets of them. So think s orbitals, p orbitals, d orbitals, and f and all that jazz. Okay, it's the same functions. And these things are symmetrized to account for the simple symmetry of the sample and also the crystal system. And a pole figure then is simply this function at, let's see what it is, fixed h and a projection, stereographic projection on y. An inverse pole figure is the other way around. It's a selected direction, and you then integrate over all of the HKLs. And they both have their uses. The Rietveld refinement then is of these coefficients. C was multiplied in spherical harmonics terms, and a sample alignment, which is because when you put the sample on the diffractometer, you don't know exactly how you positioned it. So you have to have three variables for the omega, pi, phi for the orientation of the sample. Okay, so here's an example. This is a nickel titanium shape memory alloy. It has two phases, so-called B2 and a B19 prime phase. And I'm not going to tell you what they are because I can't remember. B2, I think, is body center cubic. This thing is some monoclinic. The sample has wire symmetry, and it was positioned like this with the beam coming in this way to it and the detector here. Okay. So as I say, the diffraction rings show high spots and low spots because of the texture. And because of the symmetry of the situation, you only need to look at 1/4 of the image because the other 3/4 are the same symmetry. So instead of doing a full integration around that slice, you do it in sort of cake-shaped pieces. So you wind up 10 patterns. And you do the texture analysis, and you get a whole slew of these coefficients, and you generate then the inverse pole figures, which look like this. And so this tells you the distribution of the HKLs for the 001 inverse pole direction. That's along the wire axis. And then these things, it's a little hard to tell what they actually represent, but they're things like 111, 100, 010, for the here. This would be 111 and so forth. And for the B19 phase, there's a really strong texture for that. And that sort of gives you sort of an explanation as to what drives the shape memory effect as well. This is because you're messing with the texture of the crystallites, then they revert back. The pole figures would all look like bullseyes, and so it really got boring. So the information sequence is in the inverse. Okay. Another subject, stacking faults. So, well, the common sort of the typical material with stacking faults is kaolinite, which comes from southern Illinois, Iowa, down there around the bottom end of Illinois. That's where these guys come from. Some of them also come from Georgia. Anyway, lots of kaolinite around the world. Kaolinite consists of these layers of silicon or oxygen, which are loosely bound to each other. And so this layer and this layer are not coupled together very strongly. So they tend to slide back and forth relative to each other along some direction. That one doesn't actually show it very well, but that shows one layer on top of the other. And what that does is in reciprocal space, instead of getting points for the diffraction spots, you get streaks. Okay, and then when you look at how that streak looks like in a powder pattern, you could get this characteristic curve of where it rises and then has a long tail on it, because that's you scanning through that streak for some of these reflections. And then there are other reflections which are sharp because they're not streaked. So you have this mixture of sharp reflections and streaky reflections. So the modeling inside GSAS-II allows you to place these layers relative to each other and then simulate what the pattern should look like. And then you match it up by simply adjusting the position of the layers relative to each other. Okay, small angle scanner. Heard all about that this morning. Then I give you another look at it with respect to what's in GSAS-II. And basically, there's a range of tools available to you. One is, here's your data, and you can get a size distribution, which is basically, that is a sort of like a Fourier transform of the diffraction data. You get a distribution that looks like this. So for this particular sample, the distribution actually has two different sizes in it. And you can then model that by choosing particle dimensions and particle sizes and the amount of them to give you a fit to the data. And these kinds of parameters are fine. If you've got a lot of these, you can use sequential analysis, which is a main feature of GSAS-II, to fit one of them, get a reasonably good fit here, then say, okay, do all the rest of these in sequence. Basically, what you do is you take the parameters that you got here, copy it to the next one, do the fit, then copy those new ones to the next one, do a fit, So the expectation is just the sequence doesn't change too much from one to the next, because that's the way you do measurements. It doesn't bounce around. And then you get this table of the sequential results. And you can pick one of these columns, any one of them, and plot them versus whatever the independent variable is. And that will then give you how whatever varied from one of these patterns to another, depending on what you did to the conditions. Okay, and one more, which is if you're looking at proteins, they have a rather characteristic small angle scattering pattern, which depends on their shape and size. And the protein molecules, they all tend to be the same, for a given protein. So what you would like to do is to find out what the shape of that object is, because you might not know the crystal structure. So the process is to make a size distribution. It's a lot like that size distribution that I showed you earlier for all the paired distribution sizes in the object, which is this is the distances between pairs of atoms, and it has a distribution that looks like that. You then fit it by the so-called bead model, which begins with a sphere of beads and then manipulates them back and forth to see if it can reproduce this curve by shifting the beads about. And so here's a case where it has shifted it out and created something that looks like a donut. And there's the real crystal structure of that particular protein. And this was done by a fellow by the name of Badger a little while ago, not too long ago, in a program called Shapes. And I simply took his program, with his permission, of course, and implemented it in Python inside GSAS-II. And put a wrapping around it so you could interact with it. Anyway, what's next? Reflectometry. Now, you might ask, where am I going with this? I think I want you to remind you is that the name of the package is GSAS, right? And that stands for General Structure Analysis System. And so small angle scattering and reflectometry are parts of the structure analysis. And so that's why it all belongs together. Not only that, but by having these things in here, people who are used to doing powder diffraction may say, well, I wonder if what would happen if I did small angle scattering on it. And they can simply use the same tool that they were using for powder diffraction to do small angle scattering or reflectometry. I'll make one other comment. The code, there's something like 200,000 lines of Python in GSAS-II. I don't know what you're doing, somewhere around there. 3/4 of it is for powder diffraction. And there's probably 2,000 lines for small angle scattering, and 500 for reflectometry. So it tells you how much simpler those two things are relative to powder diffraction. Just the size of the code. Okay. A reflectivity curve. This is where you have a flat surface sample and you bring a beam in at a very shallow angle, scan one way or the other, and look at the resulting reflectivity curve that comes off of it. And if you're down low enough, then what you get is so-called specular reflection, where the beam simply bounces off the surface, completely unaffected. And that's this little piece up here. Then after that, you'll get these ripples, which will depend on whatever's in the surface. You You don't see anything if the surface is simply the same as the bulk. But if you put a layer of stuff on it, or multiple layers of stuff on it, then you'll get interference between what's in the layers of stuff and what's in the bulk. And that gives you then ripples in the reflectivity. So we then model this with substances which are layered on top of the surface. The surfaces, the bulk is here. Then there is another layer of stuff here, and another layer of stuff here, and then you're to the vacuum on the outside. So the reflection is done off of this side of the surface. So you can define whatever these components are. Doesn't make any difference what their structure is. What matters is their composition. They can be repeated. You have multiple layers. So you can define whatever the thickness is, this, and also a roughness, which has to do with whether the layers intermix right at the interface, whether there's any sort of blending of the two materials. And so that determines the sort of the nature of this part of the curve. And you can then do a refinement. And this, by the way, is a result of a fit, and there is the observed data and then the fitted curve, which actually nails it in that case. And here's a case where we have 25 layers of something, I can't even remember what it is, on top of the surface. And the variables are the width of the layers and whether they mix. And here is the observed curve, with this one with the blue one, and the fitted curve is the green one. It does okay, except for here and here. All right, what more do we? Cluster analysis. This is, again, something completely different. Now, this goes by a lot of different names, which are sort of buzzwords of unsupervised machine learning. People love that because it sort of relates to AI and all that stuff. Or pattern recognition, that's another. Cluster analysis is used in a whole lot of different fields for all sorts of things, whether it's the shapes of maple leaves to the sizes of stamps and stamp collections, just all sorts of things like that. But in our case, suppose we're faced with 1,000 powder patterns that someone handed to you, well, they didn't hand it to you. What you did is you made the measurements of 1,000 powder patterns of working for a mining company. They sent you ore samples, and you want to know which one of these ore samples got ore in it. Now, you could be really tedious and go through 1,000 Rietveld refinements or phase analysis and whatever to determine which ones they do. The simpler way is simply to do a cluster analysis on the powder patterns without knowing a thing about them. Because what you want to do is to group things which are similar. Say, okay, I've got this batch, which is over here, and I've got this batch, which is over here, and this batch, which is over here. And then when I'm done with that, I'm going to pick one out and take a look at it and say what it is. And then I'll say, okay, that one's got ore in it, and these two don't. You save yourself a lot of work. So you want to group similar data that is somehow different from the other data. And there may be clusters of these, and there may be some bad ones. So you want to be able to detect all of that. And you know nothing about it, except it's powder data. And as a consequence, there's not one magic recipe for doing this. There's a whole bunch of tools for doing cluster analysis that depend on the detailed nature of the thing that you're looking at and what it is you want to find out. And you basically have to try them out. it can be very fast, thousands in a few seconds. And GSAS-II will do cluster analysis on both powder patterns and also PDFs. It will not do images. Sorry. There are some requirements. You don't want to compare apples and oranges, so all the data sets have to be collected the same way. Same radiation, same instrument, same step size, all that sort of stuff has to be the same. Otherwise, the cluster analysis will pick out the difference in your data collection technique and not what's of interest. Okay? Don't mix X-rays and neutrons for the same reason. Neutrons would be in that group, X-rays would be in that group. So what? Okay. So here's the process. Each pattern then is considered to be a vector with thousands of dimensions, because there's a dimension for each point in the powder pattern. So imagine this sort of hyperdimensional space. Your one data set is a vector. The next data set will be a different vector in a slightly different direction if it's similar, or a vastly different difference if it's quite different. So they'll either group together as a bunch of vectors here and another bunch of vectors there. And you want to know, well, how do I know this one's a part of this group? Well, you measure the distance between the end of this vector and that vector. And if it's small relative to that distance, then it belongs in this group rather than that group. What do we mean by distance? Well, from here to here in a straight line is the so-called Euclidean distance. On the other hand, there's something called city block, which is the number of steps along each of the dimensions to get from one point to the next. So in this case, it would be here and then here. That's the city block. Cosine of the angle between them. If it's 1, then they're associated. If it's much smaller than 1, a different correlation coefficient, and etc. Because there's 11 different methods available to you for picking out what is meant by distance. And some of them are more contrasty than others, so you have to just sort of try them out and pick out your favorites. Distances again. So here's the data set of 108 powder patterns of tungsten trioxide taken at a range of temperatures from room temperature to 1200 Kelvin back down. And stuff went through a bunch of phase changes going up and back down again. Now, what you'd want to do with this data set, of course, is study the change in the crystal structure from point to point. But I'm just using it as a demonstration of what clustering can do with it. So here's the powder data. This is the distance matrix measured as, I don't know, it may have been Euclidean distance. And you get this funny pattern that looks like this. And if you look at it long enough, you can sort of say, well, obviously, this is because the temperature went up and then back down again or something like that. And you get this similarity that data sets over here are similar to ones over here because there's the same temperature, either going up or going back down again. Right? Right. So you might very well expect when you do cluster analysis that everything that's along here and everything that's along there is going to wind up in the same group because they're done at the same temperature, whether you're going up or down. The other thing you can do, or the other thing that's done in GSAS-II, is it calculates the distance from one data set to the next, just in the serial. Now, that's not useful for random data, but it's certainly useful for something like this, where you ramped up the temperature and ramped it back down again, because every time there was a blip in this thing, there was a phase change. Because if you think about it, the distance from one pattern at one phase one crystalline phase, and the next crystalline phase is going to be radically different because the patterns will be different. Whereas if the phase didn't change, the next one is going to be pretty similar. So it's one here. So there's a phase change here, one there, one there, one there, one there, one there, one there. Easily picked out. Okay. If you take this array of distances, multi-dimensional thing, and do a so-called principal component analysis, which tries to find the things that change the biggest along some dimension, and you can then classify them that way. So if you measure that, do it that way, and it's usually the first couple of 2 or 3 dimensions. If it's 2 dimensions, you get a 2-dimensional plot. If it's 3, of course, you get 3, and your points spread out in 3-dimensional space. And in the temperature variation will cause them sort of all to cluster in long strings as it changes from one to the next at the same temperature. And then when you have a phase change, you get a group of them in a different place because they're different. Okay, so that's, you know, that's one way to try to pick out what a cluster is. Another way is the so-called dendrograms, which asks, does the data have a hierarchy? In other words, is that data set somehow related back to its parent, so forth. So you sort of start here and you can work your way back and see how they split up according to whether they're related to each other. The scale here is the data set numbers. These are not in order, by the way. They are completely different. And you can sort of see, what have we got here? So the high temperature phases tend to be in this particular group down here. The low temperature phases are there. And you can almost split it up into, down through here, this is about 1, 2, 3, 4, 5, 6, 7, 8 phase changes, which you should see 4 up and 4 back down. Hindsight's better than foresight as well. Okay. Then there's the other problem is you've got a group of these points in this principal component analysis plot. And you say, well, how do we know they are in a group? Well, there's all sorts of ways of doing this, which is how far are the component points from some central point? Or can you group them by putting little Gaussian 2-dimensional curves on them? And that gives you a group that way. That's what this is about. Or you do it by measuring the density of spots around some central point. 5 minutes? Okay, I'm about done anyway. And there's all sorts of ways of doing this. But all these tools are available to you to try out. And you know, a lot of times you'll just get gibberish out of it. But sometimes it'll say, oh, that's how they're grouped. Okay, last thing is what happens if you got bad data? Well, there is a measurement that I sometimes show, which is there's 800 powder patterns, which are a steel bar collected at Lance, I think it was, at the neutron source, in which they sort of stretched and contracted the beam with steel bar about a dozen times. And the synchrotron source is not on all the time. It goes off for whatever reason. Lightning strikes in the mountains in Los Alamos, and who knows. And so the beam goes off, and so you can barely see them in here, but there's these sort of little faint lines, which don't seem to have anything in them. That's where the beam dropped out. So those ought to show up as bad data. And so there's a grouping in the cluster analysis thing where you can actually try to spot these Here's one way of doing it, and here's a rather poorer way of doing it. There's three different algorithms inside GSAS-II for finding outliers. And the way it works is you then have this plot, and then you put your cursor right on the point, set a bad point. And there's a table that shows up. Oh yeah, it's that data set. That was bad. Yeah, I stopped.